Now going to talk about another constraint that one can put on a set system. It's again somewhat different in character from the ones we've had up to now. Particularly it's contrasted with the condition where we wanted any two sets to intersect. Now, although we'll allow sets to intersect, what we want to do is make the intersection not too large. This is actually the second time I've recorded this video because, most annoyingly, the first time, although I wanted the intersections not to be too large, I accidentally gave an entire lecture talking about whether the intersection was not too small. But that's life. It turned out that the proofs were very similar, and so I didn't notice that I'd made that mistake. So let us do things properly this time. So a good title that summarizes what we're talking about is well-separated set systems. And let me be a bit more precise about what we're going to ask for. So I shall take a collection of sets. There'll be subsets of 1 up to n, and they'll all have size n over 2. And I'll put the condition that if I take two distinct sets in this collection, then their intersection should have size at most, this is the bit that I got wrong in the previous recording, at most alpha n. Turns out this is a much more interesting constraint to impose than asking for at least. Of course, everything depends on alpha. So let's just think a little bit about how things might depend on alpha. And a good way of getting some kind of purchase on the question is to think about what happens if you pick two random sets of size n over 2. Well, then their expected intersection size will be n over 4. And so it turns out that whether or not alpha is bigger than a quarter or smaller than a quarter or equal to a quarter makes a huge difference to how large the set system can be. And I'm going to start with the case where alpha is just a little bit bigger than a quarter. So the condition will be, so how big can A be? So if alpha is greater than a quarter, let's write alpha equals a quarter plus epsilon. So my condition is that when I pick any two sets in the set system, then their intersection shouldn't be too much larger than it would be if you just chosen the sets at random. And what we shall see in this case is that we can really get an awful lot of sets that satisfy this condition. And the way to see that is, let's just pick any old set of size n over 2. Now I shall choose another set, also of size n over 2, uniformly at random. We're going to ask, what is the probability that this constraint is not satisfied? So what is the probability that A intersect B has size greater than a quarter plus epsilon n? And I'm only interested in upper bound, so actually I shall just turn that greater than into a greater than or equal to. If I can get an upper bound for this, then I've got an upper bound for the strict inequality. So let's let it'll be convenient to let m be a quarter minus epsilon n. And that's because we got that if, so then A intersect B is greater than or equal to a quarter plus epsilon n if and only if A complement intersect B, and A complement is another set of size n over 2, has size at most m. So I want to know what is the probability I pick a random set B that it intersects A complement, which is just another arbitrary set of size n over 2 in at most m. We can write down an explicit expression for this. So the number of possible sets B is n choose n over 2. And so that's what I need to divide by. And then I want to count the number of sets that intersect A complement in at most m. And that's just given by something actually called the hypergeometric distribution. Sum r equals 0 to m of the number of ways of intersecting A complement in R. So that is n over 2 choose R. And then the number of ways of intersecting A in whatever's left. And whatever's left is n over 2 minus R. So R of the elements intersect A complement, the remaining n over 2 minus R elements of B intersect A. And we're just interested in an upper bound. So I'm going to, using one of the estimates from last time, I shall give an upper bound for this of root n over 2 to the n. And I'll give an upper bound of this quantity here. I'll give an absolutely trivial upper bound of 2 to the n over 2. This is the number of subsets of a set of size n over 2 of size n over 2 minus R. So it's at most the number of subsets of a set of size n over 2. Actually, why don't I do a little bit better than that? I shall say 2 to the n over 2, but I'll divide that by a square root n over 2, because I can't quite remember what the various constants are in here. I shall put an extra factor 2 there just to be on the safe side. And then what's left is just the sum r equals 0 to m of n over 2 choose R. Now the first part of that is, that all simplifies, and so I'll get that 2 and as a root 2, so I can put a 4, let's say, and then 2 to the n over 2 and 2 to the n becomes 2 to the minus n over 2, and I'll stick with this thing here, sum r equals 0 to m of n over 2 choose R. Now remember, m is n over 4 minus epsilon n, and in the last video, the one about various different estimates, the one I've already mentioned in connection with the middle binomial coefficient, we had the following inequality. It was sum s equals 0 to n over 2 minus epsilon n choose s with a 2 to the minus n is less than or equal to e to the minus epsilon squared n. So I'm going to plug that in. And what do I have to do? What do I have to choose, because I've got an n over 2 instead of an n. And this epsilon n is 2 epsilon times n over 2. So I have to replace the n by an n over 2 and the epsilon by a 2 epsilon. So I end up with e to the minus 2 epsilon squared n. So that is less than or equal to 4 times e to the minus 2 epsilon squared n. Just to say once again where that came from. That came from using this expression with n replaced by n over 2 and epsilon replaced by 2 epsilon, because epsilon n is 2 epsilon times n over 2. So that's the probability that a random set B intersects A in more than, or upper bound for the probability that intersects it in more than a quarter plus epsilon n. Now, there are two ways we can complete this stage of what I want to talk about. One is a probabilistic method. So what I shall now do is pick A1 up to AN independently at random from n over 2. Let's call a pair ij bad if I doesn't equal j and ai intersect aj is greater than or equal to, right, let me make sure I get this right. Yes, is greater than or equal to a quarter plus epsilon. And it would be tragic if I got it wrong yet again. But my inequality is the wrong way around. So the probability they intersect really quite a lot more than they would do on average. And so the expected number of bad pairs is less than or equal to the total number of pairs times the probability that each pair is bad, which is at most 4 times e to the minus 2 epsilon squared n. So we can find, this is going right back to the very first thing I talked about in this course. If the average is at most that, then we can find A1 up to AN such that the number of bad pairs is less than or equal to n over 2 times 4 e to the minus 2 epsilon squared n. Now, if the number of bad pairs, what we'll do is a very standard technique in probabilistic combinatorics. You say the expected number is not too big. If the number of bad objects is sufficiently small, then we can just throw away something from each bad object and end up with no bad objects. So in this case, the objects are the pairs. So if the number of bad pairs is less than or equal to n over 2, then we can throw away a set from each bad pair and still have at least n over 2 sets. And if we've thrown away a set from each bad pair, there are no bad pairs left. And what does that mean? That means that there are no pairs I and j, I not equal to j, such that ai intersect aj is greater than or equal to a quarter plus epsilon n. In other words, we have the well-separated set system that we wanted. But it just remains to do one last thing. So for this to work, we need the inequality that the number of bad pairs is less than or equal to n over 2. So we need and n choose 2 is at most n squared over 2. So we don't need this technically, but it is enough if that number there is less than or equal to n over 2. And I can do a little bit of cancellation. So I'll cancel an n first of all, and I'll cancel this over 2. So I've got a 1 there. And so that tells us that perhaps this need is an OK if. So OK if n is less than or equal to 1/4 times e to the 2 epsilon squared n, little n. Now the main thing I want to draw attention to here is that this is an exponentially large number of sets that we've got here. So even though the sets are really pretty far apart, we've managed to find exponentially many of them. Now, I mentioned that there are 2 ways of going about things, and actually it turns out that in this particular problem, the technique of choosing random examples and throwing away a few bad objects is a bit more complicated than it needs to be, because instead we can do the following thing. We're going to choose our sets greedily. So all I mean by that is I'll pick A1, I'll find A2 such that A2 does not intersect A1 in more than 1/4 plus epsilon times n. Then I'll pick A3 that doesn't intersect either of those 2 in more than 1/4 plus epsilon n, and I'll keep going until I get stuck. So I get to an, and then I can't find an an plus 1 that intersects all those. Now, what can I say about the point where I get stuck? Well, each AI rules out how many sets. At most, let's go and see. We looked at how many sets could intersect a given set in more than 1/4 plus epsilon n, and the bound that we got for it was 4 times e to the minus 2 epsilon squared n times 2 to the n. So at most 4 e to the minus 2 epsilon squared n times 2 to the n sets. So we're not going to be stuck unless n times 4 e to the minus 2 epsilon squared n is greater than or equal to 1. So that says n. We can get up to n equals, or give or take integer parts, 1/4 e to the 2 epsilon squared n. So for this particular problem, it's not always the case, but for this particular problem, just choosing greedily gives the same bound as choosing randomly and throwing a few things away. Okay, I'm now going to pass to the case where, let's just go back to the beginning. We've looked at the case where alpha is greater than 1/4. Now I want to look at the case where alpha is less than 1/4. So I'm going to make the sets even more separated. This time they're going to be so separated that they intersect actually a bit less than they would do if you chose the sets randomly. So now what if alpha is less than 1/4? And we're going to use an idea that is extremely useful all over combinatorics, and it's the following idea. Think of sets as vectors. Exclamation mark, just because I care about it that much. So there are lots of ways of thinking about sets as vectors. We can think of them in particular, we can think of them as vectors in f2 to the n, vectors over the reals, vectors in some other vector space. And maybe the most obvious way of thinking of a set as a vector is to replace the set by its characteristic function, something that we've already sort of discussed when talking about the discrete cube. We replace a set by a 0, 1 sequence. But again, the 0, 1 sequence can live in f2 to the n or r to the n, depending on what's convenient. So in this case, remember we're talking about sets that are of size n over 2. A rather nice way of converting a set into a vector is to associate with the set the function fa, defined as follows. I better just be strict about this. Let's say what its domain is. So it's going to be from 1 to n to the reals, and fa of x equals 1 if x is in A, and minus 1 if x is not in A. So not 0. It's closely related to the characteristic function of A, but we'll have it as minus 1 instead of 0 when x is not in A. And the nice thing about this is that it averages 0. I find that convenient. Now let's have a look at one nice thing about this is that we can relate A intersect B to the inner product of FA and FB. So let's just have a look at if A intersect B has size at most a quarter minus epsilon n, then let's have a look at FA inner product FB. And in order to work out what this is, I'm going to do something. I'm going to draw a little Venn diagram. Just, there are other ways of thinking about this, but this is quite a nice way to do it. So here's the set A, and here's the set B, and I'm just going to write in the sizes of various sets. So A intersect B is less than or equal to a quarter minus epsilon times n. Perhaps I'll write it n over 4 minus epsilon n, which means that A has size greater than or equal to, sorry, A minus B has size greater than or equal to n over 4 plus epsilon n, which means this has size greater than or equal to n over 4 plus epsilon n. And over here it's less than or equal to n over 4 minus epsilon n. Now when we work out the inner product, we get a contribution of 1 here because the values of FA and FB are the same, and 1 here, and minus 1 here because the values are different, and minus 1 here because the values are different. When you work all that out, the n over 4, minus n over 4, minus n over 4, that all cancels. And here we get a minus epsilon n, minus epsilon n, minus epsilon n, minus epsilon n, and it's less than or equal to minus 4 epsilon n. If we now normalize by saying that GA equals n to the minus a half FA, then GA is a unit vector in L2, and we get that if GA GB is less than or equal to minus 4 epsilon, because I've divided by the square root of n twice. And so thinking about sets as vectors allows us to transform the problem, or at least to transform the problem, how many sets can we find if no two intersect, or if any two intersect in at most a quarter minus epsilon n, into how many unit vectors can we find? I mean, this is a more general problem, but how many unit vectors can we find if their inner products have to be at most minus 4 epsilon? Let's, instead of having that 4 there, let's call it delta. So new question. Once we've solved the new question, we get a bound for the old question as well. And that bound turns out to be basically as good as you can get. So the new question, how many unit vectors in Rn can there be if any two have inner product at most minus delta, and here delta is just some positive constant. Well, I'm not going to tell you the answer. I'm just going to work it out. I'm going to tell you the trick for working it out. So here we have u1 to um, unit vectors, and ui, uj less than or equal to minus delta when I does not equal j. And the trick is just to consider the sum of the unit vectors ui and its L2 norm, and for convenience we square the L2 norm. The reason it's convenient to square the L2 norm is that we can then write that as a sum over all ij of ui, uj, because it's sigma ui inner product sigma ui. And this we split into the diagonal contribution. Let's be clear about the limits from 1 to m. So we have the diagonal contribution, which is just the ui, which is 1, and that happens m times. And then the off-diagonal contribution, that's the contribution when from I not equal to j. So how many, there are m minus 1 of these. And in each of those cases, we get at most minus delta. So I shall put a delta there. I'll change that plus to a minus, and then I'll put a less than or equal to there. But there's something rather basic we can also say about this sum. It's greater than or equal to 0, both because it's a norm and because we've squared it. That's sort of overkill there. So what does that tell us about m? If we can divide through by m, which tells us that 1 is greater than or equal to m minus 1 times delta. So that implies m is less than or equal to 1 plus 1 over delta. The big surprise here is that for fixed delta, it doesn't really matter that we've got a large number of dimensions to work with. We've got a bound that is independent of the dimension. So once you go below the threshold of n over 4, so we've gone from, when you're a little bit above, we've got exponentially many sets. When we're below, we've just got a bounded number of sets. It's a huge contrast. Yeah, because once I've proved this, that also proves a bound of 1 plus, well, this delta was the 4 epsilons. We've got a bound of 1 plus 1 over 4 epsilon for the sets. I might just add quickly that supposing we can, this generalizes very easily this argument. So supposing our sets had size, well, each set has size theta n, and supposing we know that distinct sets have intersection of size at most theta squared minus epsilon n. So a bit smaller than what you get in the random case. Then again, you'll get a bound that is independent of n for how many sets like that you can choose. Now, I wanted to finish by just commenting that this bound for the number of unit vectors that you can get with inner products with a bound like that is best possible, at least when delta is 1 over a positive integer. And in order to convince you of that, I'll begin by giving you an example that shows that in the case where delta is a half. So if I want 3 unit vectors whose inner products are all at most minus a half, so I've got a nice unit circle here, and this was supposed to be an equilateral triangle, so I've chosen 3 points equally spaced around the circle. Do a little bit of trigonometry, you'll find that their inner products are all at most minus a half, and I've got 3 of them, and that's the bound that we get here. So from that, you may be able to guess that if delta is 1 over k, then the best we can do is to take the k plus 1 vertices of a regular simplex in k dimensions. And that is indeed the case. But proving it is ever so slightly tricky, unless you know a rather nice trick. So if you don't know that trick, just imagine how would you find in R3 4 points that are unit vectors that form the vertices of a regular tetrahedron. It's a slightly unpleasant calculation, but there's a trick that makes it a very, very nice calculation, which is, so we're trying to find a simplex with k plus 1 vertices in R to the k. The trick is, don't look for it in R to the k, look for it in R to the k plus 1, but a subspace of k dimensions in Rk plus 1. So trick, look in the subspace a set of x in R to the k plus 1 such that x1 plus x k plus 1 equals 0. And here we can find k plus 1 vectors that are very nicely symmetrically arranged as follows. Each of the vectors will look something like this. I'm not going to normalize them first, so they'll have minus 1 over k, minus 1 over k, and one of the coordinates will be a 1. Remember, we've got k plus 1 coordinates here. So k of them are minus 1 over k. When I add all those up, I'll get a minus 1, and that cancels out that 1. So they all do belong to this subspace. So let's just write vi equals that when this 1 is in the ith place. And now let's have a look if I does not equal j, then we get that vi vj is, well, there'll be a minus 1 over k, so minus 1 over k times minus 1 over k, k minus 1 times. There are 2 places where the 1, there's the 1 for the vi and the 1 for the vj, and then there are remaining k minus 1 coordinates where we get a k minus 1 over k squared. And in the 2 coordinates where we've got either a vi or a vj, we will get a product of minus 1 over k, so that's minus 2 over k. And that equals minus 1 over k squared minus 1 over k. And if I does equal j, so now I'm going to think about how to normalize these vectors, because that's not quite the number we were looking for. We were looking for the number minus 1 over k. But that's because these vi's aren't unit vectors. So the norm of vi squared is k over k squared plus 1 equals 1 plus 1 over k. So if I want to normalize, I'll set ui to be vi over square root of 1 plus 1 over k. And once I do that normalization, I have minus 1 over k squared minus 1 over k. And then I divide by that square root 1 plus 1 over k twice. So I get 1 plus 1 over k. And if I now multiply through by k squared, I've got minus k plus 1 over k squared plus k equals minus 1 over k. So I've constructed the simplex and proved that it does indeed satisfy this, that any 2 vectors do have inner product at most minus 1 over k. I will finish now, but I'll just give you a quick preview of what's to come in the next lecture. I'm not going to tell you the answer, but or the next video. But I want then to consider the case what happens when alpha equals a quarter. So the question there is, the constraint we place is that when I have two distinct sets of size n over 2 from my collection, their intersection shouldn't be bigger than n over 4. And this is, and in the unit vectors case, again, we're going to look about unit vectors. It'll be the question: how many vectors in Rn? I should say how many non-zero if I not equal to j implies uj is less than or equal to 0. So they're at least at right angles. Before we considered the case where they had to be a little bit more than right angles, and then we had very, very few. But you can see here we could take an orthonormal basis, so the number isn't bounded anymore. We can take at least n, and in fact we can take plus or minus an orthonormal basis, so we can get up to 2n. Can we do better than that? We shall see in the next video. So that's it for today, or for this video, and see you next time.